Hi, welcome to the Tutoring Center at Raritan Valley Community College. This video covers radicals, which is section 10.4 in intermediate algebra. We're going to evaluate some problems using radical expressions. The first one is on page 688, problem 69. If you need a refresher on the basics of a radical expression, page 652 of the textbook has this summary. We'll use this definition to help solve this problem and find out exactly what is the nth root of a number is. So this one says 15 radical 8 over 4 minus 2 radical 2 over 5 is equal to what? First, we have to note that 4 and 5 have to have the same common denominator, and for this case, the least common denominator is 20. Let's rewrite the expression, leaving room for what we need to multiply both terms with so that we have an LCD of 20. So for the first one, we'll have to multiply with 5 over 5 to get the denominator 4 to equal 20. Then the second one, we'll have to multiply that by 4 over 4 to get 5 to have an LCD of 20. We'll just multiply across numerator to numerator, denominator to denominator to get 15 times 5 is 75, and you just keep the radical 8 as is with a denominator of 20. Likewise, 2 times 4 is 8, radical 2 over 20. Now let's take a look at this radical 8. Radical 8 can be expanded inside the radical as 2 times 2 times 2. Which leads us to the definition of a radical. This happens to be the square root, meaning that if we see two of the same numbers in the radical, we can take it outside the radical, and what we'll be left with is just radical 2 inside the radicand. So to finish off our expression here, we know 75 square root of 8 is really can be substituted by the same value here of 2 radical 2. Continuing on with the evaluation, 75 times 2 is now 150 radical 2 over 20, and the rest stays the same. We didn't make any changes. And then that leaves us to carry out 150 minus 8 is 142, and then you just keep the radical 2 over 20. Then we'll just divide the numerator and denominator by 2 and get in the numerator 71 radical 2 over 10. This is problem 113 on page 689. We have the expression 1 over square root of 7 minus square root of 6. Usually we don't like to see radical numbers in the denominator, and in order to get rid of them, we have to rationalize. To do that, we examine the two terms, radical 7 minus radical 6. We have to multiply it by something. Let's rewrite the expression, but without the negative in between, because the complement is an expression similar except with this operation in reverse. In this case, we have a negative sign as the operation, so we will do the reverse of that, which is addition. What we do to the bottom, we have to do to the top, because that is the multiplication identity, so that we don't change the original expression. Let's evaluate it by multiplying numerator to the denominator. So the numerator will just be 1 times square root of 7 plus square root of 6. And then the denominator, we take in a special concept, the binomial operation between two quantities. In this case, we recognize that the first term is a minus b times a plus b, which gets evaluated to a squared minus b squared. We note that a is radical 7 and b is radical 6. So the denominator becomes the square root of 7 squared minus the square root of 6 squared. We can use this same concept again right here to evaluate this expression square root of 7 squared and square root of 6 squared. That will give us, the numerator stays the same, the denominator now gets evaluated to be 7 minus 6, because squaring radical 7 gives you 7 by definition of square rooting and radical expressions, and the same for square root of 6. Finally, the denominator just evaluates to 1 because 7 minus 6 is equal to 1. And our solution simplified will just be radical 7 plus radical 6. This is problem 133 on page 690. It's an application problem using radical expressions. We're told that rate R at which water flows through a channel is given by the formula R equals K times radical M, where M is the slope of the channel and K is a constant determined by the shape of the channel. Suppose you have two channels, R1 and R2. R1 equals 1,500 times M1, and R2 is equal to 2,000 times M2. Now find R1 plus R2 if M1 is equal to 0.09 and M2 is equal to 0.04. Approaching this solution would be to rewrite R1 and R2 in their given expressions in the problem. So for R1, it is 1,500 times radical M. And then likewise, R2 is 2,000 times radical M2. Let's substitute the values that they gave us. M equals 0.09 and M2 is 0.04 in the equation to arrive at 1,500 times 0.09 square root plus 2,000 times M2 square root. And we know that we evaluate square root of 0.09 to get 0.3 and the square root of 0.04 at 0.2. So we'll just substitute these equivalent values of the square root, 1,500 times 0.3 for the first term and 2,000 times 0.2 for the second term. The first term evaluates to 450 and the second term evaluates to 400. When you add them together, your answer is 850 cubic feet per second. This is problem 50 on page 723. Given the expression cube root of a times b to the fourth plus 2 the cube root of a to the fourth times b, we're asked to simplify the expression. First, we need to expand the exponents inside the radical. The first term then becomes the cube root of a times b times b times b times b. And the second term will be 2 times the cube root of a times a times a times a times b. Now, by definition of the cube root of a number, we know that we can take out triplicates of the b's and a's and place it outside the radical. So for the first term, let's get rid of the 3 b's inside the radical and put them outside. For the second term, we'll get rid of the 3 a's and put that outside. So you see what we're left with inside the radical for the first term is just a times b, and for the second term, it's a times b. Proceeding, we have b cube root of a times b to a cube root of a times b. Now we see that there's like terms in the expression. It's ab square cube root. So if we take that term out, we will have the cube root of ab times b plus 2a, which are these terms. Or if you like, it's b plus 2a quantity times radical a times b as the solution, since usually the radical expression is after the constant.